In this video, we'll try to understand how to find out the frequency of vibration in case of spring mass system. Now we have shown the spring over here which is having a stiffness of K, and when the mass is applied or it is subjected to the mass, then there will be a static deflection by an amount of delta as shown over here. Now, if this particular mass is displaced in the downward direction by an amount of x, then what will happen and how to find out the equation of motion for this, and from the equation of motion how to find out the frequency of oscillation or frequency of vibration of this simple spring mass system that we can easily calculate. So let us start with this particular figures. So here we have shown only the spring which is having a stiffness of K, then it is subjected to the mass m, or mass m is attached, and because of that there will be a static deflection of delta. Now the weight of the mass, it will always act vertically in the downward direction, so W is equal to mg, and that will be nothing but equal to spring force, so that it will remain in the equilibrium. So spring force is nothing but it is the product of K into delta, because stiffness is nothing but it is force upon deflection. So this F is nothing but this K is nothing but it is spring force, that is F divided by delta, and therefore F will be equal to K into delta. So that we have shown over here. So we can say that this particular downward acting force, that is nothing but W, or weight that is acting in the downward direction, that is mg, is equal to K into delta. Now using this particular all these forces, now we'll draw the free body diagram for this third case. So in the third case, we have done what we have done over here is that now we have displaced this spring, we have displaced this particular mass by an amount of x in the downward direction or in this particular direction of motion. So for this case, we have drawn the free body diagram. That is for this third figure, we have drawn the free body diagram. So weight is acting in the vertically downward direction, that is W is equal to mg. Now inertia force, that is mass into acceleration, that is m into x double dot. So x is the displacement, then x dot will be the velocity, and x double dot will be the acceleration. So mass into acceleration, that is x double dot, will be the inertia force which is acting against the direction of motion. Similarly, the total deflection from this mean position, that is this particular reference position, is delta plus x. So spring force will be equal to K into x plus delta for this position, that is the position that we have shown in this particular figure. So applying the equation of motion over here, that is the Newton's law, we can apply over here. We can also apply the D'Alembert's principle over here. So mx double dot is the inertia force, then K into bracket x plus delta is the spring force, and weight is acting in the opposite direction. So the forces which are acting in the direction of these inertia forces, they are considered as positive, whereas the weight which is acting in the opposite direction, it is considered as negative. Now multiply by this K inside the bracket, so it is Kx plus K delta, and we have seen from our static deflection, that is from this figure, that W is equal to mg is equal to K delta. So K delta and this W, they will get cancelled out. So we are having mx double dot plus kx is equal to 0. Now divide throughout by m, so that mx double dot divided by m plus kx divided by m is equal to 0 upon m, or 0. So this m and this m will get cancelled out. So this x double dot plus k upon m into x is equal to 0, where x is the displacement, x double dot is the acceleration of the mass, and k is the stiffness of this particular spring which we have used over here. Now using this equation of motion which we have derived, we can easily find out what is the frequency of vibration of this displaced mass position. So comparing it with the equation of simple harmonic motion, in physics we have seen that this x double dot plus omega square x is equal to 0, that is the equation of simple harmonic motion. Now compare with the equation of motion that just now we have obtained. So we can say that this omega square is equal to this k upon m. Therefore, taking square root on both the sides, we can say that omega is equal to root of k by m. Now omega is nothing but it is 2 pi f. So f is equal to, transfer this 2 pi on the other side, it is 1 upon 2 pi square root of k by m in hertz or cycles per second or oscillations per second. So this is the frequency of vibration of this spring mass system. Thank you very much for watching.